I want to start with a very simple, almost obvious observation. But if you stop and think about it carefully, it's quite terrifying. Humans are getting better and better at killing each other. If you go back in time to the most primitive forms of conflict, when there were no weapons and everything happened at close range, hand to hand, a person's capacity to inflict damage was extremely limited. You could hit someone, you could injure them, and in some extreme cases you could kill them, but it was almost always one-on-one, with clear limits on physical strength, endurance, and distance. But then humans began inventing tools. And the interesting thing is that every technological advance didn't just help us do something better. It also helped us cause harm more effectively. Let's fast forward to the time I live and work in World War II. Here, you start to see a fundamental shift. A soldier with a rifle was no longer limited to a few meters. The effective range of a rifle was around 300 to 500 meters, meaning you could kill someone whose face you couldn't even clearly see. And that completely changed how humans make decisions. When you don't see the direct consequences, you act differently. Then things were pushed even further with the machine gun. A machine gun could fire about 600 rounds per minute. Think about that. No longer a single action, but a continuous stream of energy being released. In battles like Stalingrad from 1942 to 1943, casualties reached around 2 million people. That was no longer individual confrontations. It was the crushing power of large-scale weapons systems. And then we took war into the air. Bombers allowed one person or a small group to drop enough energy to kill thousands in a single mission. No longer specific targets, but entire areas. A clear example is the bombing of Tokyo in 1945, where around 100,000 people died in a single night. If you look at all of this from a physics perspective, you start to see a very clear pattern. We continuously increase the amount of energy released, increase the distance from the source to the target, and increase the scale of impact. Those are the three main variables: energy, distance, and quantity, and over time, all of them have been maximized. And if you look at war that way, it starts to resemble an optimization problem, not about who's right or wrong, but about how to deliver the most energy to the most targets from the greatest distance in the shortest time. And that's probably what makes it intellectually fascinating to me and deeply troubling from a human perspective. And then, if you think what we've just discussed is the peak, no, it's only the beginning. Because in the mid-20th century, humans did something completely different. Not improving old weapons, not increasing speed or range, but going straight into the structure of matter itself. In the Manhattan Project, we physicists began working with an extremely simple but extremely dangerous idea. If you could release the energy locked inside the atom, you would have an enormous source of power. Not double, not 10 times, but far beyond anything humans had ever controlled before. And that stopped being theory when the 2 bombs were dropped in the atomic bombings of Hiroshima and Nagasaki. Hiroshima, about 15 kilotons of TNT, and around 140,000 people died. Nagasaki, about 20 kilotons, adding another roughly 70,000. Those numbers aren't just statistics. They're evidence of what happens when you convert a very small amount of mass into energy. The equation E equals m squared isn't just a beautiful symbol in textbooks, it's a doorway. With just a tiny amount of mass, you can generate enough energy to wipe out an entire city. And if you think that was the limit, you're wrong again. Because in the 1950s, humans didn't stop at atomic bombs. We developed thermonuclear bombs, or H-bombs, based on fusion, the same process the sun uses to generate energy. These bombs were 100 to 1,000 times more powerful. And then in 1961, the Soviet Union tested the Tsar Bomba with an explosive yield of about 50 megatons of TNT. No longer kilotons, megatons. An entirely different order of magnitude. A bomb like that doesn't just destroy a city. It could erase a vast region from the map. And at this point, you have to stop and realize this is no longer war in any traditional sense. This is no longer 2 sides fighting each other. This is humans learning how to harness energy at the most fundamental level of matter and using it to destroy themselves. And if you think that after reaching that level of energy, humans would stop, reconsider, or at least slow down, reality went in the completely opposite direction. The world entered a new phase, commonly called the Cold War, lasting from around 1947 into the 1980s, where the two superpowers, the United States and the Soviet Union, did not directly confront each other in full-scale war, but continuously clashed in an arms race centered on nuclear weapons. And the strange thing is, when you have weapons capable of wiping out entire cities, even entire nations, the logic of war begins to change in a very counterintuitive way. You no longer fight to win in the conventional sense. You start building a system in which using the weapons means both sides are destroyed. That's what people call the doctrine of mad mutually assured destruction. It sounds like a paradox, but it became the foundation of strategic balance for decades. The idea is very simple. If one side launches nuclear weapons, the other still has enough capability to retaliate before being completely destroyed, and the end result is both sides disappear. No winner, no loser. Only total destruction. And when you think about that from a physics perspective, it stops being just a political concept. It becomes an unstable, dynamical system. A system where even a small perturbation can trigger an irreversible chain reaction. It's like a nuclear chain reaction in physics. When one neutron hits a nucleus, it releases more neutrons, and those neutrons hit other nuclei. The process self-amplifies, accelerates, and without control mechanisms, it explodes. In the case of nuclear war, the neutron isn't a physical particle, it's decisions. One missile launched triggers the opponent's warning systems. Those systems, designed to respond in minutes, are forced to decide, retaliate or be destroyed. And when retaliation happens, it triggers more from the other side. You're the chain of events where each step increases the probability of total destruction. No room for delay. No room for reconsideration. And throughout the 1980s, the total number of nuclear warheads worldwide peaked at around 70,000 units. 70,000. A number so large it almost loses visual meaning. But you don't need all of them to cause catastrophe. Even a small fraction would be enough to fundamentally alter living conditions on the planet. And that's when the real question starts to become interesting in a disturbing way. Not how many people will die in the initial blasts, but what happens afterward. In the early 1980s, scientists began studying a scenario called nuclear winter. The idea is very simple. When many nuclear explosions occur simultaneously, they don't just destroy cities. They incinerate everything: houses, forests, fuel, building materials, and produce massive amounts of smoke and soot. Those particles get lofted into the upper atmosphere, where they can persist for a long time without being washed out by rain. And when enough accumulate, they start blocking sunlight. If you reduce the amount of solar energy reaching Earth's surface, you lower temperatures. Early models suggested global average temperatures could drop by 10 to 20 degrees Celsius. That's not a normal winter. That's a phase shift in the entire climate system. And when temperatures drop that sharply, plants can't photosynthesize effectively. Plants die. When plants die, herbivores die, and then carnivores die. The food chain collapses layer by layer, not because bombs keep exploding, but because the foundational energy source of life, sunlight, has been interrupted. This means the consequences of nuclear war aren't just military. They're not just political. They're ecological. The entire life support system of the planet gets pushed into an unstable state. And what really bothers me isn't the numbers, even though they're frightening enough. It's the structure of the system we've created. We've built a system where the fate of billions of people depends on a chain of decisions that can unfold in just a few minutes. There is no physical mechanism guaranteeing those decisions will always be rational. There is no law of nature preventing human error. Physics just does what it always does. If you release energy, the energy will spread. If you create a chain reaction, it will continue until there's nothing left to react with. And that leads to a conclusion I'm not sure you'll like. The problem has never been physics. The problem is that we've placed the power of physics into a decision-making system that we ourselves know is imperfect. If you trace back the entire chain of events we just analyzed, from nuclear winter, from mutually assured destruction, from bombs that can erase entire cities, you'll realize something quite uncomfortable. None of those things are the starting point. They are the end point. They are the final outcome of a process that began somewhere very different, very quiet, and very familiar. War doesn't start with weapons. It doesn't start with explosions. It doesn't start with pushing a button, and it certainly doesn't start with a missile launching into the sky. It starts when humans stop talking to each other in a way that can resolve problems. Imagine two people in disagreement. The first thing they do isn't to attack each other. They exchange information. They offer reasons, arguments, facts. Each tries to convince the other they're right. If that process works, the problem ends there. No one gets hurt. No energy is released in the violent sense. This is how science operates. You propose a hypothesis, others test it, and ultimately data decides. But humans don't always accept data. Sometimes belief outweighs evidence. Sometimes emotion overrides reason. Sometimes honor, power, or fear makes admitting error impossible. And right at that point, the nature of the debate changes. It stops being a process of seeking truth. It becomes a contest over outcomes, not who's right, but who wins. When you shift from right to win, you've left the world of information. You've entered the world of force. At first, that transition is very subtle. It might be pressure. It might be threats. It might be economic or political punishment. But those aren't enough to force the other side to change behavior. You escalate one more step. You use violence. And from that moment on, everything becomes simple in a very cold way. No more arguments. No more facts. No more trying to change minds. Only one goal. Force the other side to stop. And the only way to do that is to impact them in a way their biological system cannot withstand. That's violence from a physics perspective. You deliver energy into a system, the human body, at an intensity beyond its capacity to absorb. The result is damage, loss of function, or death. When you understand this, you start to see clearly that all forms of war, from the simplest to the most complex, are just variations of the same principle. A punch, a bullet, a bomb. They differ in form, but are identical in essence. They are all different ways to store energy, release it, and transfer it to a target. And once you accept this view, something else important emerges. Technology doesn't create war. It only makes the process more efficient. The root lies in humans, in how we handle disagreement. When we can't resolve it with information, we switch to resolving it with energy. And from that point onward, everything is almost entirely determined by the laws of physics. You can increase the energy. You can increase the distance. You can increase the speed and scale. But you cannot change the nature of the process. This also explains why every advance in weaponry follows the same direction. Not because someone designed a grand plan, but because physics constrains what is possible. If you want to force another system to change state, you must supply energy. If you want to do it more efficiently, you must supply more energy, faster, or from farther away. And that's exactly what we've done throughout history. What troubles me isn't the equations. Those equations are very clear, very consistent, and completely neutral. What bothers me is the point where we switch from information to energy, because no law of physics dictates when that switch happens. No equation says, at this level of disagreement you must stop. That decision rests entirely with humans, and once that decision is made, the rest is simply inevitable consequence. You've activated a process that physics will execute perfectly, without hesitation, without error, and without regard for the consequences to us. When you reach this point, where we're no longer talking about ethics first, but about mechanism, violence begins to appear in a very different light. It's no longer vague. It's no longer abstract. Violence, in essence, is simply the transfer of energy from one system to another in a way that the receiving system cannot withstand. It sounds so simple, it's almost too simple. But that's exactly why it's powerful. Let's go back to the most basic example. A punch. You accelerate your arm, creating kinetic energy. And when your fist collides with another person's body, that energy is transferred. Typical figures are around 100 to 300 joules. That's not a large number if you're looking at the world of machines. But for the human body, it can be more than enough. Because the human body operates within very narrow thresholds. Bones can withstand force up to a certain point before breaking. Soft tissue can be compressed or stretched up to a certain point before tearing. The brain can withstand acceleration up to a certain point before sustaining damage. When transferred energy exceeds those thresholds, the system begins to fail. And when the system fails, you call that violence. The important thing is that you don't need any moral argument to understand this. You don't need to know who's right. You don't need to know who's wrong. You only need to know how much energy was transferred, over how much time, and to which part of the body. Physics is sufficient. And right here, something very striking emerges. Violence is not a special phenomenon. It is not something outside of nature. It obeys the same laws that govern everything else in the universe. If you hit a rock hard enough, it breaks. If you transfer enough energy into a living body, it also breaks only in more complex ways. When you accept that, war begins to lose its mystical shell. It is no longer a distant concept full of slogans and symbols. It becomes an extended system of the very same basic principle. Instead of a punch, you have a bullet. Instead of a few hundred joules, you have thousands of joules transferred in an extremely short time. The bullet doesn't just carry energy. It concentrates that energy into a very small area. And when you concentrate energy into a small region, pressure rises dramatically. Tissue has no way to dissipate that energy fast enough. The result is instantaneous destruction. Bones shatter, tissue tears, internal organs are damaged. But you're still looking at the same process. Energy enters. The system cannot withstand it. The system collapses. Then you scale it up further. A grenade no longer targets one person. It releases energy in all directions through shock waves and shrapnel. A bomb goes even further, releasing energy over a wide area, affecting many systems at once. But there is no leap in principle, only a leap in scale. And this is the point many people miss. They think different weapons are different in essence, but they're not. They are astonishingly similar. They only differ in how they store energy, how they release energy, and how they deliver that energy to the target. A gun converts chemical energy into kinetic energy. A bomb converts binding energy into heat and pressure. A nuclear weapon converts a portion of mass into energy according to E equals mc squared. But at the end of the chain, the outcome is always the same. Energy is transferred into a biological system beyond its capacity to endure. And this leads to an uncomfortable conclusion. If you want to make violence more effective, you don't need to invent something entirely new. You just need to optimize three factors: increase the energy, increase the speed of transfer, and increase the range of impact. That's why the entire history of weapon development looks so similar when viewed from a distance. Not because humans keep repeating ideas, but because physics constrains the possible paths. If you want to cause a larger change in a system, you must input more energy. If you want the system to have no time to react, you must deliver that energy faster. If you want to affect many systems at once, you must expand the range. Those three levers, energy, speed, scale, are everything. And we have pulled all three levers farther and farther over time. What troubles me is not that these laws exist. They have always existed. What troubles me is that we understand them better and better, and therefore become better and better at applying them to violence. Because once you know exactly how much energy a biological system can withstand before collapsing, you can design a system to exceed that threshold precisely, repeatably, and efficiently. And that is when violence shifts from random to engineered, no longer an impulsive act, but a calculated process. And when you reach that point, the question is no longer what is violence. The question becomes, what tools have we built to control energy in that way, and how do they differ? And that is exactly where we will go next. And once you see violence as an energy problem, the concept of a weapon automatically changes too. It is no longer individual objects with different shapes. It becomes a very specific type of device, an energy amplifier. That is all a weapon really does. It takes energy that the human body can produce or store, then amplifies it to a level that a biological body could never achieve on its own. Let's start with a classic example, the bow. When you draw the bowstring, you are doing something very familiar in physics. You are storing elastic potential energy. Your muscles aren't strong enough to throw a small object far at high speed, but when you store energy in the bow limbs and release it in a very short instant, You can transfer that energy to the arrow and launch it at a velocity far greater than your natural capability. That is amplification. Nothing mystical, nothing new in principle. Just a clever way to store and then release energy more effectively. Then you move to the gun. The principle is exactly the same. You no longer use muscle energy to draw a bowstring. You use chemical energy in gunpowder. When the gunpowder burns, it releases energy very rapidly, creating high pressure inside the barrel, and that pressure propels the bullet at extreme speed. Once again, store, release, transfer energy. The only difference is that you've replaced a weak energy source with a much stronger one, and replaced a slow release mechanism with one that is nearly instantaneous. And then you arrive at the bomb. Here, you are no longer focused on transferring energy to a single small point. You shift to releasing a large amount of energy into the entire surrounding environment. But the principle still doesn't change. Energy is stored in chemical bonds or nuclear bonds, then released extremely quickly, creating shock waves, heat, and radiation, all forms of energy transfer. Bow, gun, bomb, these three look very different to the naked eye, but from a physics perspective, they are almost identical. They are all systems designed to maximize the efficiency of the process, store energy, release energy, transfer energy to the target. And this is where you see the most important thing technology has done for war. It has allowed humans to surpass their own biological limits. Your body can produce a certain amount of energy. You can run, you can jump, you can strike, but all of it is constrained by biology. You cannot swing your arm at the speed of a bullet. You cannot generate pressure like an explosion. You cannot release the energy of a nuclear reaction. But with weapons, you don't have to do that. You only need to activate a system designed to do it for you. And this completely changes the relationship between humans and violence. Previously, your capacity to inflict harm was tightly bound to your body. Now it is bound to the technology you hold. One person with a gun can inflict far more damage than many people without weapons. One person with a bomb can affect an entire area. One person with access to a missile system can impact an entire city from a very great distance. This is no longer a difference in individual strength. It is a difference in access to energy amplification systems. And if you look at history, you will see a very clear trend. Every technological step increases this amplification capability. Not just increasing output energy, but also increasing the speed of release and the reliability of the system. Early weapons required a lot of skill, a lot of time, a lot of conditions to operate. Later weapons increasingly simplified that process. You don't need to be an athlete to generate great force. You don't need to deeply understand physics to activate a complex system. Technology makes the use of energy more accessible, and therefore violence more accessible. This leads us to a very important consequence. When you can amplify energy far beyond biological limits, the deciding factor is no longer how strong you are. It becomes how far away can you reach. Because once energy has been amplified enough, distance becomes the next variable to optimize. And that is precisely the next step in the evolution of war. Not only making energy larger, but making the distance between the one causing the effect and the one receiving it greater and greater. If energy is the first variable, then distance is the second variable that completely changes the nature of war. It doesn't just change how we fight. It changes how we perceive what we are doing. When you are close enough to another person to harm them, you see them, you hear them, you see the immediate reaction. There is a direct link between action and consequence, and that link creates a natural psychological resistance in humans. Not everyone can overcome it easily, but as soon as you increase distance, that begins to disappear. When a soldier pulls the trigger from a few hundred meters away, they no longer clearly see the face of the person on the other side. When artillery fires from tens of kilometers away, they may not even know exactly what the target looks like. And when you control a weapon system from hundreds or thousands of kilometers away, you are completely detached from the physical reality of the consequences. You don't see, you don't hear, you don't feel. The only thing you receive is a signal, target destroyed. And that detachment is not a minor detail. It is a key factor that increases the likelihood of violence occurring. Because when you do not directly experience the consequences, The psychological cost of the action decreases. Decisions become easier. You no longer have to overcome the natural bodily reflex when seeing pain or death. You only need to perform an operation, a button press, a command sent, and the rest is carried out by the system. This creates a very clear separation between action and consequence. In physical systems, we are accustomed to cause and effect being tightly linked. You push an object, it moves. You hit an object, it breaks. But in modern war, the cause can occur in one place while the effect occurs in a completely different place, at a different time. Distance is not only spatial, it is also delay, indirection, fragmentation of the chain of events. And when that chain is stretched and fragmented, human perception of it changes accordingly. You no longer see yourself as the direct cause of the consequence. You are only a part of a larger process, a link in a system. And that reduces the sense of personal responsibility, not because humans become worse, but because the structure of the system allows them not to directly confront the results of their actions. As distance increases, the efficiency of war also increases in a very specific way. You can affect more targets in the same amount of time without needing to move. You can keep the operator safe while still causing massive damage on the other side. You can repeat actions without being limited by physical fatigue or psychological stress at the same level as in close combat. All of that makes war more efficient, in the very cold sense of the word. And when you combine the two factors, greater energy and greater distance, you begin to see a new form of war emerge. No longer individuals confronting each other directly, but systems interacting with each other. One system generates energy. One system transmits energy. One system receives and endures the impact of energy. Humans are still in that system, but they are no longer at the center of each individual action. They design the system, operate the system, and sometimes merely oversee the system. This leads us to the next step in understanding war. If distance creates detachment between action and consequence, and if that detachment changes how humans make decisions, then modern war is no longer a collection of individual actions. It becomes a phenomenon of systems, where processes, technology, and organizational structures determine how energy is generated, distributed, and used. And to understand that, we need to start looking at war not as a sequence of events, but as a complex system operating according to its own laws. When the distance is great enough, and the energy is strong enough, war ceases to be a series of disconnected individual actions. It begins to transform into a system. And if you want to see this clearly, there is no better example than World War II. This was no longer small armies moving slowly and confronting each other directly. It was a gigantic machine in which millions of people, thousands of factories, and countless technical processes coordinated with one another to generate and distribute energy on an unprecedented scale. When you look at war this way, you no longer ask, who is stronger in the individual sense? You ask, which system is more efficient? Which system can produce more, faster, and more reliably? Which system can sustain the flow of energy in the form of fuel, ammunition, food, information over a long period without collapsing? That is logistics. And logistics is not an accessory to modern war. It is the core of modern war. A tank does not move without fuel. A gun does not fire without ammunition. An army does not fight without food. Each of those elements is a stream of energy that must be supplied continuously. If that stream is interrupted, the entire system begins to weaken. And this leads to a very important shift. War is no longer decided by moments of individual heroism, but by the operational capacity of an entire network. Factories produce weapons around the clock. Transportation lines stretch across thousands of kilometers. Information systems coordinate millions of small decisions. Each part of the system may not look impressive on its own, but when combined, they form a machine capable of generating and transmitting energy at industrial scale. And when you reach that level, scale becomes the decisive factor. Not because scale inherently brings victory, but because it allows you to maintain pressure longer, compensate for losses faster, and adapt to changes on the battlefield. In World War II, the nations with greater production capacity, more tanks, more planes, more ammunition, had a very clear advantage. Not because each individual tank was better, but because the overall system could generate more energy and distribute it more effectively. But scale alone is not enough. You also need coordination. A large but uncoordinated system will undermine its own efficiency. That is why technology appears not only in the form of weapons, but also in the form of organizational tools. Radar, communications, encryption, decryption, all of these are ways to ensure that different parts of the system operate together. A bomber squadron does not just need airplanes. It needs information about targets, weather, flight paths, and timing of attack. A ground army does not just need weapons. It needs to know when to advance, when to halt, when to retreat. All of that is a matter of coordinating energy in space and time. And when you look at war this way, one thing becomes very clear. The individual human gradually moves away from the center of the process, not because they are no longer important, but because they become part of a larger structure. A soldier, an engineer, an operator, each performs a specific function within the system. The final outcome does not depend on any single individual, but on whether the entire system operates smoothly. This also explains why modern war is often prolonged and attritional. When two large systems confront each other, they do not collapse immediately. They wear each other down. They seek to disrupt the opponent's energy flows, destroy factories, cut supply lines, interrupt information. Victory does not come from a single decisive blow, but from weakening the opponent's system to the point where it can no longer sustain operations. And here you begin to see a new role emerge, one that was not previously obvious: science. Because when war becomes a system, understanding and optimizing that system becomes the decisive factor. Not just creating stronger weapons, but understanding how energy moves, how information propagates, how systems interact with one another. And that is precisely where scientists enter, not as outside observers, but as direct participants in designing, analyzing, and improving the war machine. When war has become a system, the next question is, who understands that system deeply enough to improve it? The answer does not lie with those directly holding guns, but with those who understand how energy, matter, and information operate. Scientists. In World War II, the role of science was no longer auxiliary. It became central to the war machine. Take radar as an example. Before radar was widely deployed, the ability to detect aircraft from a distance was very limited. But with radar, you could send electromagnetic waves into space, receive the reflected signal, and thereby determine the location of a target before you could see it with the naked eye. That completely changed the way air defense and attack worked. This was not a weapon in the traditional sense. It did not directly inflict damage, but it determined who knew what, at what moment. And that could change the outcome of an entire battle. And radar is only one example in a much larger picture. Physics, mathematics, and computing science began to be integrated into war at every level. From optimizing bomber flight paths, calculating artillery trajectories, to decrypting enemy communications. Every problem was a physics or mathematics problem, and every solution could be directly translated into battlefield advantage. One of the clearest places where this convergence is visible is at Los Alamos, where scientists gathered to develop nuclear weapons. There were no trenches, no gunfire, but there were blackboards, equations, models, and experiments designed to understand how matter behaves at its most fundamental level. The people working there were not soldiers in the conventional sense. They did not directly face the enemy, but their work determined what kind of energy could be released, at what magnitude, and with what consequences. This created a very large shift in how we think about the role of humans in war. Previously, you could say that the soldier on the battlefield decided the outcome, but in modern war, the person writing the equation may have greater influence than the person pulling the trigger. Because if you change the design of the system, you change the entire way energy is generated and used. And once the system is deployed, it operates according to its own laws, almost independently of any specific individual. This does not mean scientists are fighting in the traditional sense. They do not aim. They do not fire. But they create the tools through which those actions become possible, more efficient, and larger in scale. And here is a very striking point. Science itself is not inherently violent. The laws of physics were not written to serve war. They simply describe how the world works. But when you apply that understanding to system design, you can use it in many different ways. An equation can be used to build a power plant or to design a weapon. Physics does not distinguish between those purposes. It only provides the tools. And this is what makes the role of science in war so special. Not because science wants to participate, but because any system that seeks to optimize the use of energy and information inevitably requires science. When war becomes a systems problem, the best solvers of those problems are naturally drawn in. And once they are involved, they do not merely improve small parts. They can change the entire way the system functions. This also leads to a shift in how war is decided. Not just the quantity of troops or weapons, but the quality of the models, assumptions, and calculations behind them. A mistake in calculation can lead to failure. A small improvement in a model can create a major advantage. And therefore, modern war does not take place only on the battlefield, but also in laboratories, on blackboards, and in computing systems. Places with no gunfire, but which shape where and when the gunfire will sound. When science has entered the center of war, what happens next is almost inevitable. Energy itself becomes the weapon, in the most direct sense. Before that, all the forms of violence we have discussed, from bows, guns, to conventional bombs, were based on familiar forms of energy. Mechanical, chemical. You burn fuel, you release energy, and you transmit it. Perhaps faster, stronger, more precisely, but still within the same framework. And within that framework, there are very clear limits. You want more energy. You need more material. You want greater impact. You need a larger system. But when modern physics delves into the structure of matter, that entire framework begins to collapse, because you are no longer just releasing energy from chemical bonds. You begin converting matter itself into energy. The equation E equals mc squared is not just a beautiful mathematical relationship. It is a statement that within every tiny unit of mass, an enormous amount of energy is locked. And if you can unlock it, you step into an entirely different order of magnitude. This is not gradual improvement. This is a leap. From chemical energy to nuclear energy, from kilotons to megatons, from destroying an area to the ability to erase an entire city in seconds. And what matters is not just the numbers. It is that all the old intuitions about war begin to lose validity. Previously, scale was tied to size. A larger army created greater impact. A larger quantity of explosives created a larger explosion. But now, you can compress an enormous amount of energy into a relatively small device. Scale is no longer about physical size. It is about energy density. A single warhead can carry energy equivalent to millions of tons of explosives. A single device can produce consequences that previously required an entire campaign lasting weeks. That completely changes how power is defined. No longer, how much do you have, but how powerful is each unit you have. And when energy becomes central, war changes accordingly. It is no longer constrained by traditional barriers like distance or logistics in the old way. You do not need to transport thousands of tons of explosives to create a major effect. You only need a system capable of releasing energy at a deeper level of matter. This also blurs the boundary between war and mass destruction. When a single device can release enough energy to destroy a city in seconds, the distinction between battle and catastrophe becomes unclear. And from there, a larger consequence emerges. When energy is released at this level, its effects are no longer confined to the point of detonation. Heat, radiation, dust, atmospheric impacts, all spread outward. An explosion does not only affect the direct target, it affects the surrounding environment, ecosystems, climate. This means war is no longer a local matter between two sides. It begins to have global characteristics. Not because everywhere is attacked, but because the consequences spread beyond borders. And when multiple nations possess this capability, you can no longer view war as a series of isolated events. It becomes part of a larger system, a global system, in which energy, technology, and human decisions are interconnected. Power no longer resides in individual weapons, but in a system's ability to understand, control, and deploy energy at large scale. And that forces us to shift to a different perspective, no longer viewing war as separate battles, but as a global network where every action can ripple out and affect the entire structure. When you view war as a global system operating on interconnected energy, technology, and chains of decisions, an uncomfortable truth begins to emerge. The entire system is more fragile than we would like to admit, not because it is technically weak. On the contrary, it is extremely powerful. But it is precisely that power that makes it sensitive to perturbations. When energy is compressed to extreme levels, when the consequences of a single action can spread globally, the margin of safety in the system becomes very small. And what makes this system especially dangerous is that decision points are often concentrated in very few people. You do not need millions of people to initiate a chain of events. In many cases, you only need one decision, one order, one action performed in a matter of minutes. This is not accidental. It is the result of optimizing the system for rapid response. In a context where missiles can cross continents in short time, you cannot have a decision-making process that takes hours or days. You must shorten it. You must concentrate decision authority. But when you do that, you also create a vulnerability. Because the system now depends on the accuracy, clarity, and stability of a very small number of humans at extremely sensitive moments. And if you think about this in terms of systems physics, you will see it is a structure with very high amplification. A small input signal can lead to a very large output. A small error or false warning signal, a misinterpretation of information, a misjudgment of the opponent's intent can trigger a chain reaction that is not easily stopped. This is not abstract hypothesis. Early warning systems, command and control systems, all are designed to react quickly, but no system is perfect. No sensor is 100% accurate. No model predicts correctly in every case. And most importantly, no human is immune to error. When you combine those elements, complex technology, short reaction times, and concentrated decision authority, you have a system in which the probability of error may be small, but the consequences of error are extremely large. This creates a very special form of instability. Not instability in the sense of constant chaos, but latent instability. Most of the time the system operates normally. Procedures are followed. Signals are processed. No incidents occur. But the possibility of a rare event, a small deviation, always exists. And if that event occurs at a sensitive moment, it can be amplified throughout the entire system. A false signal can be interpreted as an attack. A defensive response can be mistaken for aggression, and the chain reaction begins. What is remarkable is that there is no physical mechanism to stop this process once it has been triggered at large scale. Physics has no concept of sorry or misunderstanding. Once energy is released, it spreads according to its laws. This makes the human factor central in a very paradoxical way. On one hand, technology has allowed us to automate many processes, but at the most critical points, the points where final decisions are made, we still rely on humans, and humans are not ideal systems. We are affected by stress, incomplete information, time pressure, emotions, personal experience. All of those factors can influence how a decision is made in critical seconds. And when you place those decisions inside a system capable of releasing energy at extreme levels, you create a situation in which consequences are disproportionate to the initial cause. A small deviation at the information level can lead to planetary scale consequences. That is the definition of a fragile system, not easily broken under normal conditions, but capable of massive collapse when encountering a small perturbation. And when you look at the entire structure from energy to distance to systems to science, you begin to see that the stability we perceive is largely the result of everything functioning as designed. But nothing guarantees that it will always be so. No natural law ensures that decisions will always be made perfectly. No equation completely eliminates error. And that is precisely what makes this entire system, no matter how powerful still, carry a level of instability that we cannot ignore. If you look at that fragile system from the perspective of dynamics, one striking feature emerges immediately. It is not only easy to trigger, but also has a tendency to self-amplify once it has begun. An action does not remain as a single isolated point. It generates a reaction. That reaction generates another reaction. And very quickly, You have a chain of events in which each step reinforces the next. In modern war, especially with the presence of high-energy weapons, this process unfolds at a speed and scale that human intuition struggles to control. An initial attack, whether real or merely misinterpreted as real, will activate the opponent's defense system. That system is not designed to think for long. It is designed to react quickly, because if you are slow, you may lose the ability to react at all. And so, a counterattack is triggered almost immediately. But from the perspective of the first side, that counterattack looks like a new attack. And thus the escalation chain begins. Attack leads to counterattack. Counterattack leads to escalation. Escalation leads to even stronger reactions. There is no clear stopping point in this chain, because each step is justified by the one before it. What makes this process especially dangerous is that it does not require malicious intent to start. It only requires a signal interpreted in a certain way, a false warning, a sensor system mistake, a decision made under conditions of incomplete information. And once the reaction chain has begun, it is very difficult to intervene from the outside. Because each part of the system acts according to its internal logic, if you have designed a system to react in minutes, you cannot suddenly demand that it stop and think for hours. The speed of the system is itself part of the problem. When you look at this through the lens of physics, the analogy to a nuclear chain reaction becomes very clear. In a nuclear reaction, an initial event releases particles that trigger subsequent events. If each event produces more than one new event, the process accelerates exponentially. It does not increase linearly. It explodes. And to control it, you need absorbing mechanisms. Control rods, moderating materials to ensure that each step does not exceed a certain threshold. But in a war system, especially at the strategic level, those absorbing mechanisms do not always exist or function effectively. Diplomatic processes, communication channels, international agreements, all are intended to slow or stop the escalation process, but they depend on humans having the time and the will to use them. And in a system designed to react quickly, time is the first thing to be shortened. This creates a very uncomfortable paradox. To prevent being attacked, you must be ready to react quickly. But it is precisely that rapid reaction capability that increases the risk of uncontrolled escalation. You want your system fast enough to protect you, but not so fast that it triggers a chain reaction you cannot stop. Balancing those two is an extremely difficult problem, and there is no perfect solution. When you put all these elements together, large energy, great distance, concentrated decisions, and high reaction speed, you have a system in which a small event can trigger a large chain reaction. And when that chain reaches a certain threshold, it becomes nearly self-sustaining, not because someone keeps pushing it, but because the structure of the system makes each next step almost inevitable. This is precisely what makes the risk truly worrisome. Not that someone actively wants to destroy the entire system, but that the system can lead itself to that outcome if a certain set of conditions is met. And when you understand this, you begin to see war not only as a matter of will or morality, but as a problem of system dynamics, where reactions, once triggered, can escape the control of the very people who initiated them. If you follow that reaction chain to its endpoint, you will see that the scale of modern war no longer stops at borders, or even at the scope of a single nation. It extends across the entire planet, not because everywhere is directly attacked, but because the systems we depend on, climate, biosphere, food chains, are all interconnected at a global scale. When energy is released at a sufficiently large level, its consequences are no longer confined to the point of origin. It spreads, interacts with natural systems, and creates secondary effects that may not have been fully predicted at first. A large explosion does not only destroy structures and lives in the central area, it generates heat, smoke, dust particles, and soot lofted high into the atmosphere. And when those particles reach high altitudes, they do not fall immediately. They can persist for a long time, disperse with atmospheric currents, and spread across the planet. That means an action occurring at one specific point can affect the sunlight received by places thousands of kilometers away. When you reduce the amount of sunlight reaching Earth's surface, you reduce the primary energy source for the entire ecosystem. Plants depend on light for photosynthesis. If light decreases, biological productivity declines. Trees do not grow normally, crops fail. When plants decline, herbivores begin to lack food. And when they decline, carnivores are also affected. The food chain does not collapse instantly like a building being demolished. It collapses layer by layer, step by step, but the final result is still widespread instability. What is notable is that these processes do not depend on whether you are participating in the war or not. Ecosystems do not distinguish between this side and that side. They only respond to changes in energy and matter. If you alter environmental conditions at a sufficiently large scale, all living systems must adapt or collapse. This makes modern war at this level a planetary phenomenon. No longer the story of two sides confronting each other, but the story of the entire Earth system being impacted. Atmosphere, water, soil, all can be altered by what began as a military action. And once those changes spread, you cannot easily undo them. There is no undo button for the atmosphere. There is no quick way to restore sunlight levels if they are blocked by a global dust layer. These processes unfold on their own timescales, months, years, and during that time, ecosystems face conditions they were not designed to endure. This also means the concept of victory becomes very ambiguous. Even if one side achieves its military objectives, it must still live in the same altered environment. There is no way to isolate ecological consequences solely within the opponent's territory. The planet has no political borders. Atmospheric and oceanic systems connect everywhere, and therefore, the consequences of releasing energy at large scale cannot be contained. A decision in one place can lead to consequences everywhere. This is one of the points where human intuition often fails to keep up with physical reality. We are accustomed to thinking on a local scale, and action here affects here. But in a globally interconnected system, that is no longer true. Effects propagate, accumulate, and interact in complex ways. A small change in one variable can lead to a large change in another variable after a certain time delay. And when many such changes occur simultaneously, you can push the entire system out of its initial equilibrium state. This brings us to an uncomfortable realization. Modern war at this level is not only humans harming each other. It is humans intervening in natural systems at planetary scale. And when you intervene in a complex system like that, you face not only direct consequences, but indirect consequences, feedbacks, and chain effects that you do not fully control. Ecosystems can absorb some level of perturbation, but when perturbation exceeds a threshold, the system can shift to a new state in which many familiar forms of life no longer exist or exist only in very limited ways. And when you look at that from a physics perspective, it is not anomalous. It is the normal behavior of a system pushed out of equilibrium. What is anomalous is that we have created tools capable of causing that level of perturbation in a very short time. And that is why planetary scale is no longer an abstract concept in modern war. It is a physical reality. If you think what we are discussing is something entirely new, only appearing when humans invented modern weapons, physics will remind you that this has happened before, not caused by humans, but by nature. About 66 million years ago, a massive asteroid, estimated to be the size of a mountain, collided with Earth in what is now the Yucatan Peninsula. The energy released in that impact was beyond any familiar human scale. It was not just an explosion, it was a planetary scale energy event. When the asteroid struck the surface at tens of kilometers per second, its entire kinetic energy was converted almost instantly into heat, pressure, and shock waves. The area around the impact point was vaporized. Rock melted, hot gases rose, and vast amounts of material were ejected into the atmosphere. But what matters is not only what happened at the impact site. What matters is what happened afterward. Dust, debris, and soot were lofted high, spread across the planet, forming a global shroud that blocked sunlight. And when sunlight was reduced on a global scale, Earth's energy system was disrupted. Temperatures dropped. Plants could not photosynthesize effectively. Food chains began to collapse. Species dependent on the previously stable ecosystem could no longer survive. The result was that about 75% of species on Earth went extinct, including the dinosaurs. This is not science fiction. It is a geological event recorded in sedimentary layers, chemical signatures, and the structure of the planet. And the most important point is, the physics of that event was nothing special in the sense of exceptional. It obeyed the same laws we have been discussing from the beginning. An enormous amount of energy released in a very short time. That energy distributed into the environment, creating direct and indirect effects. Biological systems, dependent on the steady flow of solar energy, were pushed out of equilibrium, and when thresholds were exceeded, they collapsed. When you compare that to what could happen in a large-scale nuclear war, the parallels become disturbing. Not because the two events are identical in detail, but because they are similar in physical structure. In both cases, you have a large source of energy released rapidly. You have widespread burning, producing smoke and dust. You have those particles lofted into the high atmosphere. And you have reduced sunlight reaching Earth's surface. The result is the same chain: temperature drop, reduced photosynthesis, food chain collapse. The only difference is the origin of the energy. In the asteroid case, it was a natural event. In the nuclear war case, it is the result of human decisions. But physics does not care about that origin. It does not distinguish between natural and artificial. Once energy is released, the consequences proceed in the same way. This leads to a very important realization. We do not need to imagine what would happen when energy is released at planetary scale. We already have a precedent. Earth has experienced such an event, and we know its consequences. Not in every small detail, but in overall structure. And that makes the problem much clearer. This is not a question of could it happen. Physics shows that it absolutely could. The question is whether we create the conditions for it to happen. When you place these two side by side, the asteroid on one side, the nuclear weapons system on the other, you begin to see an uncomfortable truth. Through science and technology, humans have reached the ability to recreate a type of event that previously only nature could produce. Not exactly in every detail, but close enough to trigger the same kind of systemic consequences. And this brings us back to the core point of the entire story. Physics does not change. The laws governing how energy is released and spreads remain the same, whether you are talking about an asteroid or a bomb. What has changed is that humans have learned to use those laws to create events that were previously beyond our capability. And once you realize that, you can no longer view modern war as a separate phenomenon of human society. It becomes part of the same larger picture, where energy, matter, and complex systems interact according to unchanging laws, regardless of who initiates the process. Once you accept that the same set of physical laws can describe both an asteroid destroying life and a human-made weapons system, an almost inevitable conclusion emerges. Science itself carries no morality. It is neither good nor bad. It is only correct or incorrect in describing reality. When we write an equation, when we build a model, when we discover how energy is stored and released, we do not attach any moral imperative to it. The equation does not say, you should or you should not. It only says, if you do this, then that will happen. And it is precisely that neutrality that makes science so powerful, and also what makes it dangerous when placed in the hands of systems with specific purposes. A physical law does not change when you apply it to building a power plant or a weapon. An equation describing a nuclear reaction does not care whether you are using it to generate energy for a city or to destroy a city. It only describes the process. It makes no judgment. And this means that every tool built on science is fundamentally neutral at the basic level. A tool has no intent. It does not decide its own target. It does not choose its own use. All of that comes from humans. This leads to a point that is often misunderstood. When a technology is used to cause negative consequences, the science behind that technology does not become bad. It remains the same set of laws. What changes is how humans choose to apply it. And here, the role of the scientist becomes complicated in a very particular way. A scientist may understand very clearly how a system works, may predict the consequences of releasing a certain amount of energy, may calculate precisely the conditions for a reaction to occur, but they do not always control how that knowledge is used once it leaves the laboratory. When a discovery is published, when a technology is developed, it becomes part of the wider world where decisions are no longer based solely on scientific logic, but also on politics, economics, and other social factors. This creates a gap between understanding and application. You may understand a phenomenon very clearly, but not control all the ways that understanding will be applied. And that gap is where unintended consequences can arise. Not because science is wrong, but because the system using science has its own goals and dynamics. This also explains why the same technology can be viewed in very different ways. A nuclear reactor can be seen as a clean and efficient energy source, or as a potential risk. An algorithm can be used to optimize healthcare systems or to optimize weapon systems. In each case, the underlying science is the same. The difference lies in purpose and context of use. And therefore, when we talk about the role of science in war, it is important to separate these two layers. One layer is knowledge of how the world works. The other layer is the decision about what we do with that knowledge. Science belongs to the first layer. It provides predictive power, control power, design power. But it does not provide purpose. It does not tell us what to do with those capabilities. That lies outside the scope of science. And it is precisely this neutrality that creates a very different form of responsibility. Not the responsibility of the equation, but the responsibility of the human using the equation. When you have a tool that can amplify energy to the point of changing an entire system, the question is no longer, can this be done, but what will we choose to do with it? And that question cannot be answered by physics. It must be answered at another level, the level of values, of choices, of how humans decide to use the power they have acquired. If you set aside all the layers of political, historical, and emotional language and look at war purely through the lens of a physicist, you see something almost shocking in its simplicity. War, at its most fundamental level, is just the problem of matter, motion, and energy. Matter, motion, energy, these three elements are all you need to describe any act of violence, from a punch to a nuclear explosion. A bullet is not willpower. It is a mass of matter with a certain mass, accelerated to a certain velocity, carrying a certain amount of kinetic energy, and when it collides with the target, that energy is transferred into biological tissue, causing damage. A bomb is not political power. It is a system for storing energy, chemical or nuclear, and when triggered, it releases that energy in a very short time, producing shock waves, heat, and radiation. No matter what name you give it, no matter what context you place it in, the underlying physical principle does not change. This leads to a very powerful form of simplification. The things we usually consider complex strategy, tactics, different weapons are actually just variations of the same basic principle. How to move energy from one place to another as efficiently as possible to produce the desired effect. A bow stores energy in the deformation of its limbs, then releases it to propel the arrow. A gun uses the chemical energy of explosives to accelerate the bullet. A missile uses thrust to carry energy over greater distances. A nuclear warhead uses reactions at the atomic level to release energy with extreme density. But if you look past all those details, you still see the same structure: store energy, control its release, and transfer that energy to the target. This does not make war less serious. On the contrary, it makes it clearer. Because when you strip away the layers of rhetoric and symbolism, you see exactly what is happening. You see that every weapon, regardless of form, is a tool for controlling the flow of energy. And when you understand that, you also understand that every improvement in weaponry is fundamentally an improvement in controlling these three factors: increasing the amount of energy that can be stored, increasing the efficiency of energy transfer, and increasing the ability to control where and when that energy is released. This creates a unity that may not be obvious at first. A punch and a nuclear explosion differ so vastly in scale that they seem incomparable, but they do not differ in principle. Both are processes of transferring energy into a biological system beyond its capacity to withstand. The difference lies in the amount of energy and the way it is distributed. And it is precisely this unity that makes physics such a powerful tool for understanding war. It allows you to see through surface diversity and perceive the common structure beneath. It allows you to ask questions in a quantitative way. How much energy, over how long, over what area, with what efficiency? And when you start thinking that way, you realize that many aspects of war can be described and even predicted using basic physical principles. But at the same time, this simplification carries a notable psychological consequence. When you view war purely as an energy problem, you remove many of the elements humans typically use to justify or oppose it. You no longer talk about glory or justice. You talk about energy transferred into human bodies and the environment. That can create distance, a sense of coldness, but it also brings clarity. It forces you to confront the physical reality of what is happening, unfiltered by language, and in that clarity you see that all weapon systems, no matter how complex, rest on the same foundation. A foundation that does not change over time, does not depend on culture or nation. A foundation defined by the laws of nature, laws we have learned to understand and then learn to use. But here is the point where all physical simplification begins to collide with a far more complex reality. That system, however neatly described by matter, motion, and energy, is not operated by equations but by humans. And humans, unlike particles in an ideal model, do not always behave rationally, consistently, or based on data. If you have ever done science, you know the standard process. You have a hypothesis, you gather data, you test, you correct. If the data does not match the prediction, you do not argue with the data. You change the model. That is how the scientific system self-corrects. But when you move to human decision-making in high-stress situations, that process is not always applied. Humans are not perfect information processors. We are influenced by emotions, pre-existing beliefs, time pressure, the way information is framed. A decision may be made not because it is best supported by data, but because it feels right in the moment, or because it aligns with what the decision maker already believed. This is not a rare flaw. It is a common feature of human cognition. And in most everyday situations, that system works well enough. It allows us to react quickly, make decisions without analyzing every variable. But when you place that same cognitive system in a context where the consequences of a decision can spread on a very large scale, its limitations become clear. An ambiguous signal may be interpreted in the worst possible way. Missing information may be filled in with assumptions. Pressure to act quickly may cause verification steps to be shortened or skipped. And because the system we have discussed earlier has very high amplification, small perceptual errors can lead to actions with very large consequences. What is important here is that error is not an exception in the human system. It is inevitable. No human, no matter how well trained, can avoid error entirely in every situation. We can reduce the probability of error. We can design processes to detect and correct mistakes, but we cannot bring that probability to zero. And when you combine that reality with a system capable of releasing energy at extreme levels, you have a situation in which the reliability of the entire system is constrained by the limits of the very humans operating it. This creates a fundamental tension. On one hand, we have built tools with ever-increasing precision and power. On the other hand, we still rely on an imperfect cognitive system to control them. The gap between those two is where risk emerges. And this does not only apply to the highest level decisions. It permeates the entire chain of the system, from interpreting sensor data to communicating information, to understanding the opponent's intent. Every step can be influenced by human factors. A misunderstanding at one point can propagate to others. A false assumption can become the basis for subsequent decisions. And because the system reacts quickly, there is not always enough time to go back and verify each step. This does not mean humans cannot make rational decisions. We do it all the time. But it does mean you cannot build an absolutely safe system based on the assumption that humans will always act perfectly. Physics can give you precise laws. Engineering can give you reliable systems. But the human element always carries a degree of variability. And when that variability interacts with a system capable of large amplification, you must account for the possibility that decisions will not always be based on complete data, will not always be optimal, and sometimes will be wrong. That is not a moral judgment. It is a description of the limits of the system we are using. And once you acknowledge that limit, you begin to see that any system dependent on human decisions in high consequence situations carries an unavoidable level of instability. Many major conflicts do not arise from things that can be clearly verified, but from things far harder to measure: beliefs, ideologies, and the ways humans interpret the world. And when those become the foundation for decisions, you enter a space where the tools of science begin to lose traction. In science, if two people disagree, you can design an experiment, gather data, and let the data decide. You may be wrong, I may be wrong, but ultimately reality will provide the answer. But in belief systems, especially those tied to identity, history, and a community's understanding of itself, there's not always such a test. You cannot easily measure right or wrong in the same way you measure velocity or energy. And when there is no shared mechanism of verification, each side can believe with absolute certainty that they are correct. This creates a very different form of conflict from disagreements that can be resolved with data. You are no longer arguing over numbers. You are arguing over meaning, values, ways of seeing the world. And in that space, reason does not disappear, but it is no longer the only tool, or even the decisive tool. A clear example of this in the time I lived through is the Vietnam War. This was not just a military conflict. It was a collision of ideologies, different views on politics, society, and how a nation should be organized. From the mid-1950s to 1975, that war lasted decades and resulted in the deaths of roughly 2 to 3 million Vietnamese people, along with tens of thousands of American soldiers. Those numbers are not just statistics. They are evidence that when conflict is rooted in foundations that are hard to verify, it can prolong and escalate in ways that neither side can easily prove to end. Each side had its own reasons, its own beliefs, its own interpretation of events. And because those beliefs could not be tested by a simple experiment, there was no clear endpoint that everyone agreed on. This creates a very hard to break loop. When you believe you are right, you tend to interpret new information in ways that reinforce that belief. Contradictory data can be ignored, doubted, or reinterpreted. And the other side does the same. Two cognitive systems operating in parallel, each reinforcing itself. In such a context, conflict is no longer just about resources or territory. It becomes about defending a worldview. And when that happens, the willingness to accept risk and sacrifice often increases, because you are not just defending a physical position. You are defending an idea you believe is true. And that brings us back to the limits of the scientific method in this domain. Science is very powerful at answering questions of what and how. But it does not automatically resolve questions of should, what we should do, what we should believe, what goals we should pursue. When those questions become central to conflict, you cannot simply add more data and expect everyone to agree. You need a different mechanism to mediate disagreement. And if that mechanism is not strong enough or not accepted, conflict can shift from words to actions, from debate to coercion, and ultimately back to exactly what we described at the beginning, the use of energy to impose will. What is notable is that in such cases, the technology and science themselves still function perfectly. Weapon systems still obey physical laws. Models still correctly predict trajectories, energies. But the larger system, the human decision-making system, does not operate according to the same logic. And it is precisely the mismatch between those two layers that creates a situation in which extremely precise tools are controlled by dynamics that are not fully grounded in verification. When you look back, you see that conflicts based on belief are not exceptions in history. They are a recurring pattern. And in the modern context, when the tools we hold are more powerful than ever, that pattern carries far greater consequences than before. One of the clearest drivers is resources. Land, water, energy, raw materials, things that can be measured, counted, specified by numbers. I want what you have. You do not want to share. And so conflict begins. At this level, war can be understood almost like a distribution problem. Who controls the resources? Who has access? Who decides how they are used? Such conflicts, though still brutal, have one particular feature. They are tied to concrete things. You can point to what is being disputed. You can, at least in principle, imagine a solution of division or negotiation, because the object of dispute has a clear shape. But even here, physics is present. Resources ultimately reduced to energy and matter. Water to sustain life. Fuel to generate energy. Land to produce food. And so, at a deeper level, this is still a story of who controls the flow of energy in the system. Another driver, more subtle but no less powerful, is power. Not just having something, but deciding who decides. Power allows you to shape the rules, distribute resources, and influence others' behavior. This is not always tied to a specific physical object. It is a property of social systems. And when power becomes the goal, war may not end even when resources are divided, because the issue is not just how much, but who controls. But then you move to another layer of drivers, where things become far harder to grasp. Abstract ideas, ideology, belief, honor, identity, worldview. These are things that cannot be weighed and measured the way you measure resources. You cannot put one unit of ideology on the table and split it in half. And precisely because of that, conflicts based on these elements tend to be harder to resolve, because there is no shared reference point that all sides agree on. Each side can believe they are defending something non-negotiable. And when that happens, traditional conflict reduction mechanisms, negotiation, division, compromise become less effective. What is interesting and also troubling is a trend. The more abstract, the greater the potential danger. Not because abstract ideas themselves have greater physical energy, but because of how humans respond to them. When you fight over a piece of land, you can calculate costs and benefits relatively concretely. But when you fight for an idea you believe is absolutely true and unchangeable, there is no clear limit to how far you are willing to go. You are not just defending a resource. You are defending a way of understanding the world, a part of identity, and that can reduce the willingness to compromise. When you combine this with what we have said about technology and energy, you have a particularly dangerous situation. The tools we hold allow us to release energy on a very large scale. But the decisions about using them can be driven by factors that cannot be verified in the same way. An extremely precise physical system controlled by dynamics that can be very ambiguous. And in that combination, the risk lies not only in the capacity to cause harm, but also in the lack of a clear mechanism to stop. Because if the goal is something abstract, with no specific endpoint, then there is also no clear stopping point. This does not mean all conflicts are the same, or that every driver carries equal weight, but it reveals a common structure, from concrete, measurable things to abstract, hard to grasp things. And as you move along that axis, the ability to control and resolve conflict tends to decrease, while the willingness to escalate may increase. And once you understand that structure, you begin to see that the question is not only what tools do we have, but what kinds of goals are we using them to serve? Because the very nature of the goal, concrete or abstract, will shape how the conflict evolves and the level of danger it carries. Most wars do not begin with someone openly saying they want to cause casualties. They usually start with ideals: defending freedom, defending security, defending a system of values, a way of life, a future believed to be better. Those words sound noble, and in many cases, the people who believe in them genuinely think they are doing the right thing. But if you follow that process to its endpoint, you do not see those ideals on the battlefield. You see people wounded, killed. You see cities destroyed. You see ecosystems harmed. There is a vast gap between the starting point in language and the ending point in physical reality, and that gap is exactly where the paradox exists. What is spoken at the beginning, ideas, values, goals, does not directly translate into what happens at the end. What actually happens at the end still comes back to the basic principles we have discussed: energy released and transferred into human bodies and the environment. An ideal does not cause casualties, but actions taken in the name of that ideal do. And when you look at the decision-making structure, this paradox becomes even clearer. The people making the decisions are often not the ones who directly bear the physical consequences of those decisions. There is a separation between where the decision is made and where the energy is released. An order can be issued in a safe room, based on maps, models, scenarios, but the consequences of that order unfold somewhere else to other people. And this is not necessarily due to malice. It is a feature of how the system is organized. Large scale requires hierarchy, requires division of roles, but that very division creates a psychological distance. When you do not directly experience the consequences of an action, the way you evaluate that action can change. This connects directly to what we have said about distance and detachment. Distance is not only physical, it is perceptual. It is the way the system allows a decision to be separated from its consequences. And when you combine that with abstract drivers, you have a situation in which ideals can be sustained at the level of language, while physical consequences accumulate elsewhere. A person can continue to believe they are pursuing a legitimate goal, even as evidence of negative consequences becomes increasingly clear, because those two layers, the layer of ideas and the layer of physical reality, are not always directly linked in their experience. This does not mean every ideal is wrong or that every decision is irrational, but it does mean there is an asymmetry between the way we talk about war and the way war actually unfolds. The language of war can be abstract, symbolic, even moral. But the reality of war is always concrete, physical, and unavoidable. And it is precisely that asymmetry that makes the entire phenomenon so hard to grasp. Because you can be convinced at the level of language without fully imagining the consequences at the physical level. You can agree with a goal without clearly seeing what the path to that goal will look like in reality. And when you place this in the context of modern tools capable of releasing energy on a very large scale, the paradox becomes sharper. Ideals can remain unchanged in speech, but the physical consequences of pursuing them can far exceed what anyone initially envisioned. And when you look back at the entire structure, you begin to see that war is not only a matter of technology or strategy. It is a matter of how humans connect or fail to connect between what they believe, what they say, and what they actually do in the physical world. Matter, motion, energy, they still operate in the same way they have operated for billions of years, the way they operated when an asteroid struck Earth, the way they operate in every device we create. No exceptions, no flexibility to suit our desires. If you release a certain amount of energy under certain conditions, the consequences will unfold exactly as those laws dictate. What has changed and continues to change is our ability to harness those laws. Technology does not stand still. It advances, sometimes in small steps, sometimes in large leaps. The capacity to store energy, to release energy, to transfer energy more precisely, faster, farther, all of that continues to improve. And if you look at the trend, there is no sign that this process will stop. Each new generation of technology opens possibilities that did not exist before. Some of those possibilities bring clear benefits, cleaner energy, more efficient systems, deeper understanding of the world. But along with that, those capabilities can also be applied in other ways. And this is the point where science, with all its precision, stops. It can tell you what is possible. It can tell you what will happen if you do a specific thing. But it does not tell you which path among those possibilities you should choose. That question is not a physics question. It is a human question. And so, if there is one question left after everything we have discussed, it is not can we do this? The answer to that question, in many cases, is yes. The real question is, what will we do with that capability? Will we use our understanding to minimize risks or to accept them? Will we design systems to slow dangerous reactions or to accelerate them? Will we try to connect what we believe with what actually happens in the physical world, or will we continue to keep those two layers separate? No equation answers these questions. No single experiment can resolve them. They depend on collective choices, on the way social systems are organized, on the way information is interpreted, on the way humans, with all the limitations we have discussed, make decisions in critical situations. And perhaps the most honest thing a scientist can say at this point is, I do not know what the answer will be. I know the laws will not change. I know the technical possibilities will continue to expand. But the way those two meet in the real world, in specific decisions, is not something you can derive directly from an equation. It is something that will be determined by us ourselves, decision by decision in the specific circumstances we will face. And so, rather than ending with a firm conclusion, perhaps the more reasonable thing is to stop at that question, an open, uncomfortable but honest question. As we understand more and more about how the world works, what will we choose to do with that understanding? If you find this perspective makes you think differently about war and science, please subscribe so you don't miss the next stories. See you again. And as always, keep asking questions.